when we were talking about integrals, we studied one particularly important integral, which we called the p integral, which is the integral from 1 to infinity of 1 over x to the p. Let me remind you what we actually found. We found that if p is greater than 1, then this would be a convergent integral. And if it was less than or equal to 1, it was a divergent integral. All right, and this integral is going to be very useful because it can tell us a whole lot about a whole bunch of series if we use the integral test. So let's consider the series 1 over n to the p from n equals 1 to infinity. Now, let's think about a few cases. If p is less than 0, that means that we have a negative exponent. Then notice this actually looks like n raised to some positive number. And if we think about large values of n raised to a positive number is going to be very large. And so the terms would be going to infinity. And if the individual terms that we're adding up go to infinity, then we would conclude based on the nth term test that this diverges. All right, so if p is less than 0, an goes to infinity, well, which definitely means that this diverges. Now, if p was equal to 0, then we basically have just n to the 0, which is 1. And if you just keep adding up 1 over and over again, well, that's definitely going to be divergent as well. And if p is greater than 0, then 1 over n to the p would be a function that has a positive exponent in the denominator. And so as n grows, the denominator grows, which means this is going to be a decreasing function. It would also be positive. And for n greater than 0, it'll also be continuous. And so we can apply the integral test in that case. And if you recall from our previous videos, the integral test says that if the integral converges, the sum converges. If the integral diverges, then the sum diverges. And so within this case, p greater than 0, we have two cases. We have p that's greater than 0 and less than or equal to 1. And notice, if we look at our integral, that would be a divergent case. And then we also have p greater than 1, and the integral we showed earlier in the course converges. And so of all the values of p, the only way that we can actually get this sum to converge is if p is greater than 1. Okay, so to summarize, the sum from n equals 1 to infinity of 1 over n to the p converges for p greater than 1, and it diverges otherwise for p less than or equal to 1. And we did that by applying the integral test and the nth term test. All right? Now, on its own, that series is not particularly interesting. However, it is a very, very useful tool for comparisons. And so one of the things that we're going to look back at the next batch of videos is we're going to look at a variety of different sums that are going to be hard to evaluate with integrals. They're not going to be geometric. They're not going to be telescoping. And so one thing that we can do is we can compare them to 1 over n raised to the p. And since we now know exactly when that converges, we can determine when other related series converges. All right, so before we wrap up, let's just make sure we understand this result. If I have the sum from n equals 1 to infinity of 1 over n squared, well, that's the Basel problem that we looked at in the previous video. And according to this, p is greater than 1. So it must converge. And if we have the sum of 1 over n to the 1/2, then p is equal to 1/2, which is less than or equal to 1. And so we can conclude that it diverges. And so we don't need to do any extra work there. This result, which is known as the p-series, so we have the p integral, this is the p-series, can allow us to take shortcuts for sums of this form. And we derive this result focusing on the case where our integral starts with 1 and the sum starts with 1, but actually that applies more generally if we change this to any integer k greater than 1, then it would still hold. So this is a result that works for really any starting value, since it's really the tail, the large values of n, that ultimately dictate whether it's going to converge or diverge.